All right, so there are a number of somewhat unique topics that we will be seeing along the path to understand Bitcoin's cryptography. So we're just going to introduce these here in this video, starting with modular arithmetic, which is really just a way to loop together a set of numbers and do calculations. So nothing more than think about doing math with a clock. So if you were to solve this question, pause the video if you need to, how would you walk through solving this question? 7 p.m. plus 30 hours. I'm just going to skip through this. So this is pretty straightforward. So you would probably go, well, 7 p.m. plus 24 hours brings me to 7 p.m. tomorrow. Then I'm just going to add 6 more hours. That takes me now to 1 a.m. So what you just did was modular arithmetic, or you just did arithmetic in modular 12. And the terminology is such. The 12 is called the modulus, and 6 is your remainder. And it's usually written out, so this is a more detailed way of looking at it. It means you are going to be dividing the modulus by some whole number. So in this case, you divided 2 times the modulus 12, and then you use the remainder 6 to equal the number you started with, 30. And a lot of times it's written like this, which is saying that 30 is congruent to 6 modular 12. This is the modulus, this is the remainder, this is the number that you started with. And the same concept applies to any number, and the formal way to express it is here, and the remainder is placed here. And what this means is, for all of these, is it's be 12 times some number plus 6 equals this. 12 times some number plus 2 equals this. 7 times some number plus 5, is congruent to 40. And so back to our clock. Here we have mod arithmetic and modulo 12, and then the basic add, subtract, and multiply is straightforward. So here you just add, or you can subtract here to get a result, and then once you had that result, you just apply the modulus. And then same thing with multiplication. Once you have the result, you apply the modulus. And what this closed group gives us, what the modulus gives us, it's a way that when we know that we can always find a remainder, 6, 8, 6, 8, 3, we can always find a remainder that's going to be within this group. So next is finding an inverse, because there's really no division per se in modular arithmetic. It's a process rather known as finding the inverse. We're going to use this circle as an example. We're going to use a prime number. So here's our prime number, 19. And sometimes this is referred to as a group, just because when you circle the numbers around this way, especially when it comes to a prime number, this construct here actually grows a number of interesting relationships, a lot of them very useful in cryptography. So a lot of times this goes by group. And for a number, if you want to find the inverse of a number, in this case it's 13, inverse of a number modulo 9, in this case is 13, but there's a process you're going to have to go through. And also sometimes the inverse is written like this. It's called 3 to the negative 1, or 3 inverse. And what the process you're going through is you're searching for some number that when multiplied by 3 is going to equal 19, your modulus, some multiple of 19, and a remainder of 1. And there's more to this piece now. This remainder of 1 we're not going to cover, but just know that these conditions must be met in order to have the inverse of a number within this circle. And in this case, it's 3 times 13, which equals to, or is congruent to 19 times 2, 38, plus 1. And it's formally written like this. And if you have this, then you know that this inverse in this group exists. And in this group, we have several such relationships. But you see, not every number will have an inverse. And as we go towards more cryptography, we'll come across groups that really only have a couple, and that's fine. But an inverse is not a guaranteed thing. And here's a closer look at the process we go through. Or I'm sorry, backing up. this is just showing some interesting properties we come across when we start going inside of these prime circles. So here, as an example, our number 3. This is giving you a little sneak peek into how we go through the process to find the inverse. But we can take 3 and multiply it by every number inside the circle, and then take the modulus of that result, and the answer is going to be every single number inside the circle. And this feature, or this result, has a lot of cryptographic applications. And then, you know, when it comes to the inverse, there's many cryptographic schemes and many constructs we're going to look at in the course of encryption and decryption. You're going to have a secret number somewhere inside this circle, and there's going to be some equation you have to go through that's going to require us to have the inverse of that number. So it's during the initial setup is when you select your secret number, and then you check to make sure it actually does have an inverse before proceeding any further. So whatever protocol that you have, you know is going to work. And the check for an inverse, which is something we're going to see several times, and we're going to use small numbers as an example, where we are using small numbers, but at Bitcoin and cryptography in general use numbers that are hundreds of digits long, if not thousands. But small numbers are easy, and the math is still the same. And here we have the number 3. And what happens is almost suspiciously simple. You just start at the first number, multiply 3 by that number, and you're looking for an answer to this equation that gives you a remainder of 1. And so you start with 1, get the answer, and you go down and check what's the remainder. And here we can see the remainder: 3, 6, 9, 12, and so on. And finally, yes, we do find a number that gets the remainder of 1. In this case, the answer is 13. And computers have a very fast method to do this, to find an inverse, but computers are still essentially just checking every number. Just the process looks a little different. And that's it now for inverse. These are some recurring key ideas. Try to use examples on this because modular arithmetic it's not that complex or involved, but it really is hard to see and visualize, which can create a big hurdle. But hopefully the examples can get us over that. So for the first one, we're going to use modulus 18, and we have 2 different numbers here. We have a and b, well, I guess 3, and then the modulus of the 18. And what's happening here is for a, okay, yeah, for a, we've got 5. We've got 5 is congruent to 0 plus 5, and same here. The same applies here. 23 is congruent to 18 plus 5, and then that ensures this last equation also holds. Now we're moving on to a third number. We have c, which is 41, and if these 2 conditions are true, then this last one is also true. And we know from the first equation that a and b are going to land at the same number. So b is going to go around the circle just a different number of times, but they both land here. Now if we know b is here, and b is congruent to c mod m, it's the same. C is still going to land on this number. It's going to go around the number 18. It's going to go around this circle more times, but it still ends up here. And for these equations, they probably look a little wonky, and generally you're going to see the largest number on the left, and you're going to see this number here is going to be a number that's less than the modulus, so 5 being less than 18. And then all these numbers are going to be positive. That's generally what you'll see most of. But these equations here, with the negative numbers, and this one's larger than the mod, these are still correct expressions. Yeah, and this statement is still that's still a valid statement. So next, we have a is congruent to b modulo 19. And what this means is, a starts here. It's going to move around. A is 41. So it's going to move around the circle twice. That's 38. And then it's going to go the remainder 3 and land at the same place as B. And likewise, we have a D of 8, and we have C here of 27. C is going to move around the circle, and then the remainder and land in the same location. So shuffle the slide a little bit, and then we have the red and brown now on the bottom here, and we've got the blue and the green on the bottom here. So we'll start with the red and brown, and we add them together. You can see that it's going to equal 11. And if we add the actual values, it gets us to 68. And 68 is the same thing as just going around the circle 3 times. That's 3 times. And then moving the remainder of 11, which is also the values of B plus D. So we won't cover subtraction, but subtraction is essentially the same thing. And we're going to go into multiply. And when we multiply, then A times C will be congruent to C times D. And A and C multiply together. 1,107. This is, we're going around the circle 1,000. We're going around the circle 58 times, and then we're ending with the remainder of 5. And this is the same as B and D. 3 times 8. 3 times 8 is 24. 24 is 1 time around the circle plus the remainder of 5. And for the next example, the first look, this looks somewhat more involved. We'll see an example. So here we have A of 28 and B is 10. And when it comes to this piece here, for D, you need a D that is a divisor of M. So when M is divided by D, it has to equal a whole number. We're going to use 18 and 9 as our example. So for mod 18, B is 10, A is 1 time around plus the remainder of 10. And now I think this property gets really interesting. So for the big circle, here we went around the circle 1 time. Here A went around the circle 1 time. And over on the new modulus, A now goes around 3 times. And then B is going to go around 1 time, and then plus the remainder of 1. So change the slide up, and as D changes, as long as you get a whole number in the result, all you're changing is the number of times around the circle and the remainder. But this equation here, this congruence on the bottom, still holds true. Yeah, this congruence here on the bottom still holds true. And again, on this one here, this is usually going to be expressed with the smaller number, with a number smaller than the modulus. But both of these expressions are still valid. And for the last one, we're going to look at multiplication of the modulus. And in these example numbers, m of 5, n of 7, and m times n, 5 times 7, it equals 35. And A 37, B is 2. And here for A, you go around the circle 7 times plus the remainder of 2. And then here, you go around the circle 5 times plus the remainder of 2. And then B lands on top of that as well. And likewise, A and B are still going to be congruent, modulus 35. Okay, so I didn't mention this at first, but the m and n have to be relatively prime for this to work. And now we're going to get into why this is the case. So we when it comes to m and n, they cannot share a common divisor. So these are examples of good m and n's. 5 and 7, 3 and 10, 4 and 9, none of those share a common divisor. These are the bad examples. So 4 and 8, they do share a common divisor, it's 2. Same with 10 and 15, they share a common divisor of 5. these are not going to work, and we'll see how. So back to the one that does work. When it comes to A, we can take any A can equal any multiple of 35 plus 2. So 107, for example, it's now just going around 7 times 5, 7 times 5, 7 times 5 plus 2. It's going to land here every single time. And now let's compare this to 4 and 8. So these are the 4 and 8 equations. And right now it still looks like it might work. So here we have mod 4, go around 8 times plus 2. Here we have mod 8, we're going to go around 4 times plus 2. And it works here, lost my mouse, works here. We're going to go around once plus 2. So far, these wrong numbers are working. And now we need to go back and compare this again to our previous example. Oops. Go back again and compare this to our previous example. So 1, in both cases, A can take on the multiples of m times n plus 2. So this is 35 times 1, 2, 3 plus 2, and so on, and same for 32 times 1, 2, 3 plus 2. And for each value of A here, it's just representing another 7 laps around the circle, another 5 laps around the circle. These are just trips around the circle. And as you're taking these steps up the A value, you're going around each circle more. There's no shared steps until you hit 35. And when you do hit 35, all the equations, all 3 of these equations are still going to be valid. There's no shared steps. Now compare this to our wrong example. As we start to step up in A values, we do hit a shared point. And it's 16. We hit it, and we hit it pretty quickly. So we hit this shared point before we reach our multiple of 32. And what this means is we reach a point where these 2 equations will work, but this equation, this is an unworkable intermediary step. So this is not correct, and that's why you can't have numbers that have common divisors. So all said, m and n must be relatively prime, and if they are, then this equation is true. So next, another relationship between prime numbers, and also there is a surprising amount of history that's gone into prime numbers dating back to over almost 2,000 years ago. And we're going to do a lot of Fermat. We're going to see a lot of Fermat and Euler in these 2 equations that they have. So starting from the basics again, these are just the definitions again. Relatively prime is talking about a relationship between 2 numbers. Any 2 numbers that do not share a common denominator are considered relatively prime. So move that to the left. And now we have Euler's phi and a couple builds. Okay, so Euler's phi is going to count the number of relatively prime numbers. So here's your number in this column. These are the numbers that are all relatively prime to the number in this column. And this column here is just the count. Whoops, is just the count of these numbers. And this is Euler's phi. That's what this is. And Euler found this relationship. 1 is every prime number, and then 2 is a prime number, 2, 3, 5, 7, 11 here. Every prime number has 1 minus that number total relative primes. And the relative primes of 2 different numbers are also relative with multiplicity. You can multiply them together, and we'll see a couple of examples about this. So we have our 2 prime numbers here, 3 and 5. The phi of those is 2 and 4. Multiply them together, that's 8. Now if we take the phi of 15, which is 3 times 5, all of these numbers are co-prime to 15, and the total count of that is 8. So it's the same number. And another example, slightly larger, but same story. Phi minus 1, or the prime number minus 1, 4 and 6 multiplied together, 24. The prime number 5 and 7 multiplied together. These are all the numbers that are co-prime to 35, and the total is 24. So next is Euler's theorem, which is one of the concepts we'll see several times. And this is just a small example, and these are these here are the numbers relatively prime to 9. And for this, we're just going to pick one. We're just going to say A equals 2. And according to Euler's theorem, this equation is going to be correct. And it is. So 64 is the same thing as this multiple of 9 plus 1. And again, this works for any of these coprimes. And the Euler's phi multiples of these coprimes. So what you have is this works with these Euler phi numbers, these coprimes, because of their the unique relationship they have with their prime number, which is also the modulus. So next, and these two are pretty closely related and also straightforward. A can be any integer. P is going to be a prime number. I picked small ones. They're easier to work with. And that's all there is to this one. And again, this special property has to do with prime numbers and their lack of divisors. And Euler's theorem is along the same lines, but it's just a more higher level relationship. But it still does have to do with prime numbers and the amount of coprimes within a prime numbers. So Euler's phi is equal to the prime minus 1. So that's part of this relationship here. And this is a true statement. And then lastly, a couple of points on exponentiation. If you raise both sides of a congruent to the same power, it's going to stay congruent. And here it is kind of in some more detail. So the number of times you're going to go around the circle changes, and your remainder is going to change, but the equation is going to stay congruent. And also, you can go backwards with this. So if you start with each one of these have an exponent that has a shared divisor, you can just take this divisor out. And in this case, it gives you, 2 divided by 2 is going to give you 1, and you're going to end up with the original equation that we had. So there are a number of unique and probably never encountered before modular arithmetic relationships that we're going to start seeing a lot over the next several videos. And this was just an introduction.